Hi everyone, my name is Saborn Elastic Bear from the Science Lab, and today we're going to attempt to solve a specific problem from Newtonian mechanics two different ways. Let's say we have an inclined plane. Now, you already probably know the answer, right?
Friction or without friction, baby?
No friction. So this is probably already what you're thinking in your head. But
X for acceleration?
is that more clear?
Yeah, sure.
Now,
So what does that mean? Second derivative?
Yes.
Okay.
Second time derivative. So now, here's what we're going to do. We're going to place a wall here, right? And here's what we're going to do with the wall. We're going to keep nothing. We're not going to let anything come in from the... Okay. You know what? We're going to stick to...
It's okay. Go ahead.
We're going to stick to science on this channel. Now, here's what we're going to do. We're going to build a great spring, and we're going to make this block pay for it by attaching it directly to the spring. So now, what forces are acting on this box? Well, there's the force of gravity, and of course, as you know, the only relevant force of gravity is the component acting in this direction, which we'll call Fg parallel. And then there's the force, the restoring force of the spring that wants to make the ramp great again. So, let's say the spring wants to reach all the way over, well, I'm not really sure. Let's say the spring wants to reach all the way back over here, bringing the ramp back to its roots. So, let's see. How do we find exactly the equations of motion for this object? Well, we're going to change our system of coordinates. So this is the normal system of coordinates. And now we're going to rotate it so that the x direction is parallel to the ramp and the y direction...
Why you want to do that?
That's a lot easier, as you'll see. Now, here's what we can do. According to Newton's laws, the force on an object is equal to its mass times its acceleration. And now, what are all the forces in the direction that matters? Well, there's Fg parallel, which is just mg sine theta.
Minus Fg. Minus Fs.
Okay. Minus k multiplied by x is equal to mx double dot. So now you have mx double dot plus kx is equal to mg sine theta. And so you have, well, how do we solve this? There's a particular solution, which is just letting x be a constant, which means the second time derivative is going to be 0, which means that kc...
Y acceleration is 0.
No, there were two solutions to this differential equation, right? So this is the particular solution. So
Can you pull the chart, baby?
yeah. So it's the solution that when we plug it in actually solves the equation. So we have kc is equal to mg sine theta. So we're going to get c is equal to mg over k sine theta. But now we get the homogeneous solution as well, which is what happens if...
What is C stands for?
Well, it's just a constant, any constant. Now, what happens if this constant was actually 0? Now you might be asking, but mg and sine theta would never be 0. Why are you doing this? Well, when we're solving a differential equation, so you have f of, y dot, etc. over here is equal to whatever function of x over here. Here's what's going to happen. If you have y particular that solves the equation, and y homogeneous that solves it when f of x is equal to 0, that means adding y homogeneous to y particular isn't going to change the output of this, which means that this is also going to solve the equation. So let's find y homogeneous. That's just going to be equal to, well, mx double dot is equal to minus kx. So we let x be equal to e to the rt, where r is some constant, as an on-shot solution. So the second derivative is just r squared e to the rt, and well, the function itself is e to the rt. We divide by e to the rt on both sides, and we get r squared is equal to minus k over m. So r, I don't know why I put a second equal sign, is equal to I times the square root of k over m. Now, of course, we raise that to the eth power. Well, not really, but then you get e to the I times the square root of k over mt, which is just equal to, it can be any arbitrary constant multiplied by e2 times this cosine, the square root of k over mt, plus some phase shift phi, and the other part is imaginary, which means we don't really care about it. So this is our homogeneous solution, which means our total solution is just mg over k sine theta plus a multiplied by cosine of the square root of k over m t plus phi. Now, this is a constant. You can forget about it. What we really need to focus on is this, because it tells you how it's going to oscillate and by what frequency. If you increase the mass, that means the frequency is going to go down. It's going to oscillate less often. If you increase the spring constant, it's going to be more violent, and so it's going to vibrate more violently, which means the frequency is going to go up. And next time, if you want to see this done with friction as well, that's what we're going to do next time. So that's going to add a damping factor to our equation, which means that the spring's going to have to stop after some time of moving.